Now we want to learn about probabilistic method. Our first goal is to prove a lower bound on the Ramsey number that we introduced before. That we will use this probabilistic method. And what is this probabilistic method? This is weighted counting. You have certain object, discrete object, and then you want to count. And then when you count, you give some weights. So this one is you count twice. This one you count 1.5 times. This one you count once. And then you add them. Okay, so this proportion has weighted counting like 2.5 or 3.2. So that's essentially what we are gonna do. And those weights are the probability. So we consider this weighted counting as if we are choosing one of them with a certain probability, and those probability are proportional to its weight. And then you compute the probability that your chosen one is one of these sets. So that's same as weighted counting one here, right? The space that we are counting here are this discrete object equipped with the weights. And then we give them the name of this probability space. As we are only considering about discrete case, we define this discrete probability space. This is either finite set or countable set. And that together with a function p, which is this weight, and we just imagine that as a probability that is defined on the subsets of S, which is called event, such that, if we consider non-discrete one, we have to define what sets are measurable or not, but here we don't have to. We only care about the discrete space. So whenever we have A, then the probability of A happening is at most 1, the event, and the event of entire space is 1. And if A1 to A2 to these events that could be infinite, they are pairwise disjoint. Subsets of F, and the probability of which one of them happen is take the summation of the probability. Okay, so this is just formal way, but we don't, in the following discussion, we don't define this probability space. We will just say that, okay, color these. Okay, yeah, let's do it with an example. So, in 1947, Ehrlich showed that the diagonal Ramsey number, RKK, is bigger than K times 2 to the K over 2 divided by E times square root of 2. And how did he prove it? He considered the probability space, discrete probability space. And each element of this is a red-blue coloring of the edges of Kn. So what do? We consider a complete graph on Kn, and then I didn't define this n yet. And for some n, we consider it, and we color each edge with either red or blue independently with probability half. Okay, so this is not 100% rigorous statement. What it is saying is that we are considering the discrete probability space whose elements, the set S for the universe, consists of the element, and each element is a red-blue coloring of this. So for example, if you have any 3, then what? You have this these 8 coloring. And then what is said is that we give each of them the value 1/8 as its probability, which is the function, is P. And then for certain event, the probability of this 3 is 3/8. So this suggests, I mean, whenever we say that we consider something as random, that's giving us this discrete probability space. And then we are equipped with this probability. Instead of formally writing down the discrete this probability space, we just write it this way. Then it's obvious what space we are considering. And a set of k vertices is what? We consider probability that it's homogeneous. And what's the probability? Its probability is 2 times 2 to the negative k/2. If you have a k vertices that are k choose 2 edges, the probability that all of them are red is this, and the probability that all of them are blue is this. So we sum them up, then twice times this is the probability that it's either red monochromatic or blue monochromatic. And we know that since there are n choose k such events here, the probability, so this is the choice of k vertices out of this n vertices. The probability that at least one of them occurs is what? By union bound, it's at most n choose k times 2 to the 1 minus k choose 2. So if this is less than 1, then what? Then with positive probability, you will end up with a coloring which avoids all these bad events. That means there is on n vertex graph G, there is a coloring. Sorry, instead of a graph, it's coloring. Coloring of the edges of Kn with no homogeneous set of size K, as we conclude that this KK is bigger than n. Then how do we choose n to make sure that this is more than 1? Since we know that n choose k is at most n times e over k to the k, this being smaller than 1, it suffices to have that the n over k is more than 2 to the k minus 1 over 2. Why? So n choose k times 2 to the 1 minus k choose 2 is at most any k times 2 to the 1 minus k minus 1 times k over 2 times k. In order this to be smaller than that, if any over k times 2 to the negative k minus 1 over 2 is 1, then this implies this. So, but so this is sufficient for us, and what this is actually equivalent with n being what? Yeah, k times 2 to the k over 2 over e times 2 to the square root of 2. So if you just take n to be exactly this, then you have this inequality which yields this inequality. So this probability becomes smaller than 1. So this shows this bound. So that means when n is this, there is this red-blue coloring which avoids any red monochromatic KK or blue monochromatic KK. So this inequality holds. So we have this and we have this as before. So this is roughly root 2 to the k, and this is roughly 4 to the k. So there are quite a large gap between. But this is pretty much best we know. We will later improve this a bit more, but just the constant improvement. So here, this is constant, this is function on k, and we will show that we can get a better constant. But essentially, I mean, not much improvement is known. And as I mentioned, I mean, these arguments are actually weighted counting. Instead of using this probability, you can actually count the number of coloring which have such homogeneous set, and then you show that the number of such coloring is smaller than the number of entire ways to coloring, and you show that there is one exist. But that's more complicated. And then by using this probability, we can write the proof and in more clear and efficient way, and then we can think about the problem in a more effective way. So it has its advantage. Okay, let's see more application of this probabilistic method. And let's consider this proper coloring or hypergraph. What is the proper coloring in graph? Whenever you have two vertices adjacent, they get different color. In other words, once you take an edge which consists of two vertices, those two have to have a different color. So you have edge and then different color. So for hypergraph, how do you generalize it? There are two ways of generating it. One is that this edge is not, you force this edge to be not monochromatic once you color it. And the other one is you force them to have all different colors. And here you force them all different colors. So both of them make sense. But we will take the upper definition. A proper K coloring of a hypergraph H is labeling of the vertices from a set of K colors such that no edges of H is monochromatic. And we say that our hypergraph H is K colorable if there exists a proper K coloring of H. Okay. So this is a generalization of proper coloring of the graph. And here, in terms of this proper coloring, you have H if there are no edges, then, this is easy. There are no restriction. If there is one edge, then okay, you have a restriction. Or not all of them have to have same color. You put another edge, then another restriction. So as there are more and more edges, this finding proper coloring gets difficult and more difficult. So you need more and more color, more and more number of colors. That's what you saw in the graph coloring as well. Generally, if you have more edges, then you require more color. It's not absolutely true, but that's the tendency, right? Then you might want to say that, okay, at most this many edges, then can we always find the K color? Is there any such bound? In other words, you can say that if this Fk, we define Fk, if we denote this as the minimum number of edges in a K graph, K uniform graph, hypergraph, that is not certain number of colorable, let's say not two colorable for very basic case, then what it would be? So that's a natural question. So most simple case, we consider the two color repeatability, and if you are under certain number of colors, you are always two colorable, and then if you are over that, then there is this non-two colorable one. What's this threshold? For example, in graph case, what is the two colorability is bipartite graph. And then the smallest non-bipartite graph is triangle. So f of 2 is 3. And then for two edges, it's always bipartite, no matter how you take it. And for generally, if you have a K uniform hypergraph, then what would it be? This proved in 1963 that this f of k is at least 2 to the k minus 1, and most 2k minus 1 to the k, which is roughly 4 to the k. So again, you have certain exponential gap. It's somewhat analogous to the Lumley theory. And let's prove this. So we prove this lower bound using Floer's method. How do you do it? In order to show this, what do we have to show? We have to show that if you have a graph with less than 2 to the k minus 1 edges, and you can find the two coloring, proper two coloring. That's what you want to show. And then in order to show the existence of such a coloring, Floer's method suggests that you randomly color it, and then if the probability that your coloring is a desirable one with a positive probability, that shows the existence of such a coloring. So if you consider a random coloring, it's okay. Uniform random coloring the vertex, and that makes specific edges monochromatic with what probability 2 to the 1 minus k. You have a k vertices, all of them being red or all of them being blue. You add the probability, then you get it. So with fewer than 2 to the k minus 1 edges, the total probability you take the union bound. I mean, those events may not be independent, but the union bound, it doesn't matter. Of these bad events is less than 1 if the number of edges is smaller than 2 to k minus 1. So a proper two-coloring exists. So that shows this lower bound. Oh yeah, lower bound. And for upper bound, what? You want to find the one example which is not two-colorable and then have this many edges. We can do this by generalizing this triangle. We consider complete hypergraph. On 2k minus 1 vertices, and then it's k uniform. This is not two-colorable. Why? By the Pigeonhole principle, if you two-color it, some set of size k must be monochromatic. So this is not two-colorable. And this has how many edges? 2k minus 1 to k edges. So this shows this inequality. And this approximation is by Stirling's approximation. Stirling's formula, you can approximate this. Okay, but unlike the diagonal Ramsey case, I mean, you have this large gap, but we can, for this problem, we can actually improve this upper bound. So instead of finding one example, you can again utilize this probabilistic method to improve this. So there exists a k uniform hypergraph with 1 plus 0 of 1 times e log 2 over 4 k squared 2 to the k edges. That is not two-colorable. So again, this little rotation, we use it. We have big O notation, big omega notation, little rotation, little omega rotation. And yeah, you can, I mean, take it again on the Wikipedia and what it means. Here it means that this is function which goes to 0 as k goes to infinity. So what do we do? Before we randomly, so for given hypergraph, we randomly generate coloring to show this lower bound. Here, what we want to do is we will randomly generate hypergraph and then show that that is not two-colorable. That's what we will do. So for that, how do we want to do that? We want to randomly generate the hypergraph, and then we want to show that that is not two-colorable. How do we show that this is not two-colorable? We consider all possible coloring. Coloring 1, coloring 2, coloring 3, and so on. You have n vertices. What? You can color them all red. That's one coloring. And then you color the vertex 1, vertex 2 to ... to red, and then last vertex blue. That's second coloring. And so on. You have 2 to the n different way to color them. And then you randomly find the hypergraph. And then you check that okay, in this random hypergraph, what's the probability that this one give you a two coloring? 1%. What's the probability that this one give you a coloring? 1%. That if there are coloring 99, only 99 of them and 1%, then what? With probability at most 99%, one of them works. That means with probability more than 1%, there is positive probability that none of this coloring works for this random hypergraph. But we list out all possible coloring. That means that this is not too colorable. So that's the rough idea on how we want to proceed. And first, we want to compute this probability. So we consider K graph with the M edges and its vertex set being the brachytile, and where this N and M will be chosen later to optimize the resulting bound. It's often very convenient to not specify what it is, and then we determine later, because we will later see what kind of relation between those two or more are necessary. And once we see that, then we determine this. But before that, it's just some number which is not fixed yet. And for a fixed coloring, we'd say R points in a color, red, and S in the other color, where R plus S is I. And the probability that random K set. So we want to take a K from hypergraph later. So we have to choose a set of size K. And this is monochromatic with the probability R to the K plus S to the K divided by N to the K. And this is what? This is always at least N over 2 to the K plus N over 2 to K divided by N to the K. So this is minimized when R and S are same, because this, binomial function is convex. So this shows that for coloring, the sigma colors the vertices with 0, 1, 2 color. Probability that random K set of this brachytile is monochromatic is at least 2 times N over 2 to the K divided by N to the K. Let's define this to be P. I don't want to write this too many times again. So if we select M edges of size K independently and uniformly at random, so you choose them, you choose one and then you add it, you choose another, you add it, you choose third one and you add it. And in theory, choosing the same thing multiple times is okay. In your resulting hypergraph, if you have a collection of same edges, more than one hyperedge, one hyperedge is there with more than one time, and you just take one of them at the end. It doesn't matter. Because in terms of coloring, multiple edges does nothing. Then what's the probability that none of them is monochromatic? Is and most what? 1 minus P to the M. You do that M times, and each time the probability that it is not monochromatic is at most 1 minus P. And you did the M time, so you just multiply them because each time it's independent. So this is m also minus p to the m. And how many? But since there are 2 to the n distinct possible coloring, and each has what? Probability and most 1 minus p to the m of being a proper two coloring. We have an upper bound of 2 to the n times 1 minus p to the m on the probability that our set of m random edges is two colorable. The probability that one of the coloring actually works for us is at most this. So now what? It suffices to minimize m while this number is smaller than 1. The probability that it being two colorable is smaller than 1 means that there is positive probability that it is not two colorable. Since what do we know? It is more than 2 to the m times e to the minus pm. So this and this inequality holds. It suffices to have what? This one's more than 1, which is same as you take the log, then n log 2 minus mp is more than 0. So if we have this, then that's sufficient. So there are 3 variables here. Then p is actually a function of m and k, but you have n, m, k. Then there could be more than one possible value of n. So here we are interested in m in terms of k. N is just some middle variable. So let's choose. So there are these several variables. Sometimes you just arbitrarily give certain value, which feels right to you, to a certain variable. Makes the later analysis easier. So let's just put this relation to, so this is quite natural. So what's the smallest number m which satisfies this is this, right? The ceiling of that. So we're fixing this relation. Now what? Now we choose n to minimize this m. And in order that, we have to minimize n over p. So recall that p is what? P is this number. And then if you spell it out, that's right, 2 to the 1 minus k times the multiplication of n minus 2i over n minus i. And we know that this is roughly what? 1 minus I over n minus some constant times I squared over n squared. This is big O of that, which is roughly e to the negative I over n plus big O of I squared over n squared. And then assuming n is large and then k is small, you just apply this, then you get what? P is asymptotically 2 to the 1 minus k times e to the k minus k squared over 2n. Let's say this is 1 plus 0 of 1 of this, when k is much smaller function than n. So what do we want to minimize? N over this. So n over p is what we want to minimize, which is n times 2 to the k minus 1 and e to the k squared over 2n, 1 plus 0 over 1. and we want to minimize this. You take the derivative of this in terms of k, then let the derivative to be 0 to minimize this, then roughly taking n over k squared over 2 will roughly minimize this. With this choice, we just compute then what? M being, you can compute this value. So with this value and with this M, you see that this relation holds. So that with positive probability, none of the proper two coloring works for this random hypergraph. That shows that there exists hypergraph with this many edges, which is not two colorable. Okay, and maybe let me mention one of the reasons why the two colorability of K uniform hypergraph is interesting. Yes. This is related to the K-choosability, the least colorability of some bipartite graph. They are related. So this theorem is known if nk is the smallest order of non-K choosable bipartite graph, then what? You know that this relation holds, where this fk is the smallest size, smallest number of edges in the non-two colorable K uniform hypergraph, as here. Okay, so I will not prove this. I mean, you can prove this at the next slide. Okay, so that's good examples for this probabilistic method. And this probabilistic method is quite useful by using some tools from probability. There are many more things that you can do. Yeah, we will collect more tools and more group methods and then see how they give us some interesting results on graphs and hypergraphs. Yeah. Okay, yeah, thank you for listening. I will see you in the next video.